All right. Exponential functions. It's a little bit different from what you've been seeing. First semester Algebra 2, you saw linear functions, you saw all polynomial functions, where you had nice integer exponents, right? You had third degree, fourth degree, and so on. Okay? Then, after we studied polynomial functions first half, we started with other types of functions, and instead of nice integer powers, we had fractions like this. This was the chapter we just got done with. X to the 1/2 power, which we studied was the square root of x. Or we could have x to the 1/3 power, which is... All right, so now moving from here, we are going to see something today you haven't seen before. This is going to all get reversed. And now, instead of x being on the main line, my x is now going to become my exponent. So exponential functions are going to look something like this. 5 to the x power. I'm going to have 1/3 to the x power. I could have 0.2 to the x power. Those are all exponential functions. And what exponential functions look like is it kind of rides along the x-axis here, slowly increasing, and then all of a sudden it's going to blow up. We see that every winter with the flu season or a cold virus. 2 people have it, 4 people have it, 10 people have it, and then all of a sudden everybody's sick. Right? That is an exponential function. Stock market crashes, and you see an exponential decay in your portfolio, right? Your investment portfolio. That would be an exponential decay where it kind of tapers off and then just has a huge drop. So a lot of biology formulas are exponential functions. Okay, there's 2 types of exponential functions. We have a growth, exponential growth, which looks like this. It goes up, and then we also have an exponential decay, which of course goes down. Okay. So we have a growth or a decay. How can you tell the difference between them? By looking at a function. If I have some number raised to the x power, if this number right here, if b is less than 1, that is a decay. If b is greater than 1, that's a growth. Okay? So looking over here, 5 to the x power, would that be a growth or a decay? A growth, because 5 is bigger than 1. This would be a growth. What about 1/3 to the x power? Decay, because 1/3 is less than 1. What about 0.2 to the x power? Decay, very good. Okay, so growth, decay, just by looking at what number is being raised to the x power. That tells you growth or decay. Of course, the other thing we're going to do today is you can take these exponential functions and you can stretch them, you can compress them, you can shift them left and right, up and down. So we have transformations. If I have an exponential function and I'm adding or subtracting a number to that, that would be my up or down. So this is something you'd want to write on your notes, maybe in the top of your paper there. I can give you a blueprint of all your transformations. If you have a number that's small, like the x, and it's just adding, subtracting from that little x, that would be your left and right. If I am multiplying the function by a number, that of course is vertical stretch or compression. And the last is negatives, and negatives always mean reflection. We have 2 reflections. If I have a negative out front, that's going to be reflect over the x-axis. If I have a negative just to the x, that's going to be reflect over the y. Look at the first example. We're going to do 3 things with graphing. The first thing we're going to do is determine if it's a growth or decay. We're going to state the transformations and then the y-intercept, which I'll talk to you about. So let's just do the first 2 here. Number 1, would this be, and this is supposed to be written like this. The x is supposed to be an exponent. Okay. Would this be a growth or a decay? Growth. Because what number is being raised to the x power? 5. Since 5 is bigger than 1, that is a growth. Remember order of operations. Order of operations says I would do the exponent first and then multiply. So since you're doing exponent first, 5 is being raised to the x. So that's a growth. What transformations happened here? What does this negative mean? Reflect over the x. Yep. What about this 0.1? Vertical compression of 0.1. Okay? We do not say a vertical stretch of 5 because 5 to the x power, that's our parent function. That's what we started with. Okay? 5 is my b. So this is my parent function. Anything else that happened to 5 to the x, right? I'm starting with that. Anything else is a transformation. 5 is not a transformation. All right, y-intercept. Let's talk about that for a minute. Y-intercept, if you look at your functions here, we have a growth, we have some sort of decay, right? You'll see either one. A y-intercept is where it crosses the y-axis. So on this growth function, my y-intercept would be right here. On this decay function, my y-intercept would be right there, okay? How do I find a y-intercept? Y-intercept always crosses the y-axis, therefore, x is 0. Okay. So to find the y-intercept, I'm going to put 0 in for x and solve it. Mental math. 5 to the 0 power is 1, right? Anything to a 0 power is 1. So 5 to the 0 power is 1. 1 times negative 1/10 is negative 1/10. So I'd have negative 0.1. Okay. And then I can graph. And the great thing about graphing these is I'm going to let you use your graphing calculator. In my y equals, I'm going to put negative 0.1 times, not plus, times 5 to the x, right? And I can graph it. And we can see that it's going down. Why? It's a growth. It should be going up, but it's going down because we reflected over the x-axis. So my graph going up got reflected, so now it's going down. That's why you see it looks like that. So second graph, and there's going to be, you'll probably need 3 points to graph. And it's going to be a lot of decimals when you're graphing. You're not going to have nice integer points. So we know 1 point already, the y-intercept, 0 and negative 0.1. So some other good points would maybe be negative 1, negative 0.02, 2, negative 2.5. There's 3 points that are pretty good, and I graph those. Okay. And yes, there's arrows on both ends of that graph. Okay. Now I want to take another kind of time out and explain something to you. When we are graphing exponential functions, we have what's called an asymptote. Okay. An asymptote is a line on a graph that your graph will get closer and closer and closer to, but never touch. So if you notice on a growth, it starts along the x-axis and then blows up. So if I go this way with the arrow, I'm going to get closer and closer and closer to the x-axis, but I will never touch the x-axis because my function will never equal 0. There is no number that I can put in for x that's going to make this equal 0. Impossible. Because anything to the 0 power is 1. Right? So there's no x value that makes this 0. So you will never touch the x-axis. Same with a decay, right? It's going to go down, but if I follow this, again, I'm going to get closer and closer to the x-axis, but I'm never going to touch it. That's an asymptote. Your asymptote is always x equals 0 unless I have a shift up or down. If I move up 5 units, now my asymptote is 5. If I move down 3 units, now my asymptote is negative 3. And we'll study those a little bit later, but that's what it is. It's a line that your graph gets closer and closer to, but will never touch. And you can see that on your graph. If you keep going up on your table, these numbers keep getting smaller and smaller and smaller, but no matter how far you go up, you will never get 0. It'll get closer and closer to 0, but never get there. Second example here. Is this going to be a growth or a decay?
Decay.
A decay because 1/5 is less than 1. Very good. Decay. What are my transformations? What transformations happened? None.
Nothing.
Yep, none. 1/5 is your parent function. 1/5 is being raised to the x power. There was nothing else that happened, so there are no transformations there. What is the y-intercept? Y-intercept is when x is 0, so if I put 0 in for x, what happens? It equals 1. Very good. Right? So to graph this, I already have a point, 0, 1, but let's find some other points. When you put this in the graphing calculator, you do need parentheses. Parenthesis 1 divided by 5 to the x power. You need parentheses. Right? And yet we can see a decay. See how it's coming down? So second graph, go to my table. Be careful the e's. Those are really big numbers there. I don't get a number that works until -1. So -1, 5, and then I can do what? 2.04. There'd be 3 nice points. 0, 1, -1, 5, and then it's going to come down like that. All right, again, step 1, is this going to be a growth or a decay?
Decay.
A decay, because 1/3 is less than 1. Decay. 2, what are my transformations?
Reflect.
Reflect over the x, right? Negatives always mean reflection. And what?
Vertical stretch.
Vertical stretch of 5. Good. And my y-intercept is going to be what?
1.
If I put 0 in for x, what do I get? Put 0 in for x. Anything to the 0 power is 1, but 1 times -5 is -5. So I'll make a table. I have 0, -5 as a point, but now I need to find some more points. So y equals -5, and then you need parentheses, 1 divided by 3, to the x power. Graph. Yep, I can see it's a decay, but it got reflected. Go to my table. Let's see. Maybe like 2, -0.56. 5 and 0.02. Right, something like that would be good.